Thank you for reminding me. Because
No
that
problem.
somehow always, even though I have a note here that says start recording, I seem to look right past it. Okay, so just as a quick reminder, first name and last name when you go to log in to Zoom, and make it here on time. The waiting room will open at 5 to 1, and anyone that gets checked in after 5 to 1 or checks into the waiting room after 5 to 1 will be considered late. Okay, so I asked before, and I got a little.
Sorry, 5 to 1 is 105 or 5 to 1 is 12:55.
All right, so I'll open up the waiting room at 12:55. At 1:05, anybody that checks into the waiting room after 1:05 will be considered late. Is that cleared up?
Yep.
Okay. So I asked a couple of people what you had done. So let me get feedback from the rest of you. Last week we talked a little bit about circuits and that kind of stuff, and talked a little bit about scientific notation and metric prefixes and that kind of stuff. And then what did you guys do in lab? Somebody said that you were measuring resistors, and what else did you do?
We went over the colorway.
The color code?
Mm-hmm.
Okay. So you had the color code, and then, so you did color code, you did resistor values, you didn't get into component recognition at all? Or what?
Yeah, you also use these machines.
You had the circuit boards? Okay.
And we started looking into the different resistors, and like it was like introducing all the other resistors like thermal, photo, and all those type of resistors.
Okay.
Yeah.
Okay. All right. That just gives me an idea of what you did, and I can work accordingly. Let me put up a whiteboard that I'll share, and then we'll talk a little bit about where. Okay, last week, we talked a little bit about an electric circuit. We're going to get into much more depth with it as we go on. But we talked about a circuit, and we said that a circuit, we had some sort of a power source, like a battery. And we had one end which was positive and the other end which was negative. And then what we said was we had what we call a load. All right, so this was, I'll label this in a minute. So we had a power source. We had the device being powered. Which we generally call the load. And then we had wires to allow a complete path for the current to flow. And then we talked about very briefly, there were two types of current flow. There was what we called conventional current flow. Which was the movement of the net positive charge charge is through the circuit.
No subió vaina de Hansel negra.
Okay, and then we had electron flow.
Okay. ¿Tú no has visto la...
Electron flow was the movement of electrons through the circuit.
Is the movement of electrons considered the net negative charge? Or
No.
do you just say movement of electrons?
It's the movement of electrons. The electrons, remember, have a negative charge to them. And inside of the atom, we had protons, electrons, and neutrons. Neutrons were neutral. Electrons were negative. The protons were positive. But if I have an electron attached to an atom that's neutral, and I take an electron, so let's say there's 19 protons and 19 electrons. Since the charge on an electron and the charge on a proton are the same number of coulombs of charge, remember we said coulombs was how we measure charge, that means that 19 positives and 19 negatives cancel each other out. We say the atom is electrically neutral. If I remember, we talked about the fact that through a chemical reaction in the battery.
What are coulombs again?
The unit of charge.
They're the units of what?
Charge.
Okay.
Okay, so when we talked about charge, we said the designator was Q, and coulombs was what we measure the units. Okay? So if I have an atom that's electrically neutral and that chemical reaction pulls an electron into the solution, let's say, that original atom now has 19 protons and only 18 electrons. So there's one extra proton that's not balanced out by an electron. So we say that that atom has a net positive charge. All right? It's the electrons that move through the circuit. But if I move an electron, and we talked about this very briefly last time, if I get an electron that moves from one atom to the next atom, and then that electron moves, that atom has an electron that moves over, and then the next electron has an atom has an electron that moves over. We saw that in essence, the electrons were moving in one direction, but the atom with the net positive charge is moving in the other direction. So
it just kept it at like electrically neutral?
In the entire thing, it's electrically neutral, but each individual atom will, for a brief instant in time, see it go net positive. So if I had this, very quickly to go back, let's say I had an atom here and an atom here, okay? And let's say I had 19 protons and 18 electrons. And for some reason, an electron from here goes over into this atom. Actually, let me take that out and go the other way. I think that's the way I did it last time. Let's say this electron leaves to go into the solution. We're inside the battery now. So now what we've got is 19 protons and only 18 electrons. We had 19 and 19. When this electron leaves, it now becomes 19 and 18.
Okay.
So what we've got is an extra proton, which isn't balanced out by an electron. So we have a net positive charge. Now, if we have the atom next to it, which also had 19 protons and 19 electrons, and an electron goes over to here and fills the spot where this electron was, now this one goes back to 19. So this is now back to being neutral again, 19 protons, 19 electrons. But this one now goes from 19 protons and 19 electrons to 19 protons and 18 electrons. So the net positive is now over here. So the net positive atom moved from left to right as the electrons were moving from right to left. And notice the protons didn't move. The protons, the positive charges, stayed where they were. That's why we say it's a net positive. The positive charges didn't move, but because we took away an electron, we ended up with one unbalanced proton, and that means that the atom itself became net positive. So first go around, when the first electron moved, this one was the net positive atom. Then when this electron moved, this one went back to being neutral. This one went to being back to net positive. So the net positive charge moved to the right when the electrons were moving to the left.
So the protons and the neutrons are like in like the nucleus, right? And then the electrons are kind of in the shell. So is there never going to be a time when like the protons ever move?
Um,
No, because
not in anything we're going to worry about.
oh, okay.
Now, all we're going to do is, and again, this is the Bohr model of the atom. So, and we can say, as far as anything we're concerned, again, I don't want to get into the molecular level of things, but as far as we go, we're just looking at what happens with the electrons so that you understand that electrons are flowing in this direction, but positives are flowing in that direction. And we said that the electrons go from where there's an excess of electrons, the negative terminal, to where there's a deficiency of electron, the positive terminal. And net positive charges will go from where there's an excess of net positive charges to where there's a deficiency of, or an excess of electrons to balance them out. Okay.
But it does happen. It's just not something that we're going to worry about, but that happens.
I have to double check to see whether or not protons actually ever move.
Do neutrons move?
Pardon me?
Do neutrons move?
I don't think so either. But again, you're the first person that's actually ever asked me these.
Actually, in the battery where the acid is doing is powering, there is delivering of hydrogen ions, which are protons. So inside the liquid, inside the acid, the protons are moving as hydrogen ions.
Okay. There we go.
Okay. Well,
I always learn something from my classes. It's always a good thing. Okay, so getting back to what we were talking about before we get too far off topic. So then we said that we could think about, I'm going to erase this because I need to have a little space and not lose my diagram. Okay, so we said that we can think about the power source, and the power source is going to be units of voltage. We said there were three quantities that we worry about in a circuit. There was voltage, which we said was like a pressure to try and move current through the circuit. Well, let me put it this way. Electrons through the circuit. We said that we obviously had the current, which was the movement of the electrons or net positive charges through the circuit. And then we had the third part of the picture we said was resistance. And we said resistance was the opposition to current flow.
And you said resistance was inversely proportional to current and voltage, right?
Yeah, we're going to get to that. All right. So those were my three quantities. Voltage, which we said we abbreviate with the letter V. Current, which we said was abbreviated with the letter I. And resistance, which we said was abbreviated with the letter R. We said voltage is measured in volts.
Yes.
Current was measured in amperes. And resistance was measured in ohms, which we use the Greek letter omega as a shorthand for writing ohms. Okay? So that's pretty much what we went through partially last class. Let me bring up a screen so I can see who's here. Okay. Everybody good? Anybody need more time?
Mm-mm.
Okay. So then what we said was, we said that Ohm, Georg Simon Ohm, came up with what was now called Ohm's law. And Ohm's law says that the amount of current flow is directly proportional to the applied voltage. So in other words, directly proportional to the pressure trying to move current through the circuit, and inversely proportional to the opposition to current flow, the resistance. And if we do a little cross multiplication, we can see that if I cross multiply, I could write this as V is equal to I times R, or we could write this as R is equal to V over I. All right. Any of them is valid, and we're going to use them in different forms depending on what we're trying to solve for. And then we talked about, well, what happens if I, let's say, have something like, I want to find the current if the voltage is 20 volts and the resistance is, let me keep the numbers simple. 10 million ohms. If we plug it in, we said I is equal to V over R. And I remember saying you always want to make sure that, let me just, okay. You want to make sure that you always give me the formula, the substitution of the values into the formula. And then the result. So that should be 0. I think that's right. 10 to the 7th. I think I got one too many zeros in here. One too many zeros.
5 zeros, I think, right?
Yep, that's what I just said. I got one too many zeros. And we said that this is a pain in the neck to deal with. All of these zeros here and all of these zeros here are a pain in the neck to deal with. So what we came up with, we briefly talked, and this is where I think we left off. We talked about scientific notation and how scientific notation is a shorthand way of writing very large or very small numbers. Okay. And then we actually talked about metric prefixes, and we'll talk more about those in a couple of minutes. This sounding familiar? Hopefully.
Yeah.
Okay. All right. So scientific notation. How do we represent scientific notation? Whenever we have scientific notation, the format, well, let me talk about this first before I get to the format. If I have the number 3,000, is that the same as 3,000 times 1?
Yes.
Yeah. What if, is that the same as 300 times 10?
Yeah.
Yeah. Is that the same as 30 times 100?
Yeah.
Is that the same as 3 times 1,000?
Yeah.
The answer is yes. Okay. So what we've done is we've said, okay, let's move the decimal point and get rid of it, the placeholders, as powers of 10. Well, if you remember, 1,000 is 10 to the third power, because 1,000 is 10 times 10 times 10. So how many times do we multiply the 10 to get 1,000 is 3. So we can write this as 10 to the third power. Hopefully, you're all sitting here going, why is he boring us with this? Because it's so obvious and we know this already. Hopefully that's true. But invariably, I find that there's always somebody that's confused. So I always start from the ground and work my way up. So this would be the same as 30 times 10 to the second, or 300 times 10 to the first, or 3,000 times what?
10 with 0.
10 to the 0. Remember, anything to the 0 power is 1.
1.
Okay. So when we're going to write a number in scientific notation, we're always going to have the format of one leading digit followed by the rest of the digits times 10 to some power. All right. So in scientific notation, we're always going to have one number in front of the decimal point. So if I look back over here, we said that 3,000 times 10 to the 0 is 3,000, and 300 times 10 to the first is 300, and 30 times 10 to the second is 3,000, and 3 times 10 to the third is 3,000. All of these are equal to 3,000, but only this one is in what we call scientific notation, because this one is the one that's got one decimal. If we think about it, the decimal point would be there. In this one, the decimal point would be here. In this one, the decimal point would be there. So here we've got 3 digits in front of the decimal point, 4 digits in front of the decimal point, 3 digits in front of the decimal point, 2 in front of the decimal point, 1 in front of the decimal point. So this is the one that's in scientific notation. So if we have a big number, we want to just move the decimal point, keeping track of how many places we moved it until we get the decimal point right to the left, to the right of the most significant number. All right. So if I had, move this out of the way. So for example, if I had this, I want to express the number 456.8 in scientific notation. So what we're going to do is we want to get the decimal point to be here, right there.
2 places.
So we're going to move 1, 2 places. Now remember, when we move this decimal point to get from here to here, and then from here to here, the value of the power increased. So this time, if I move it 1, 2 places, that's going to mean that this is going to be something times 10 to the second power, which means that this would be 4.568 times 10 to the second power. All right. So we moved it 2 places left, which meant that we put a 2 for the power of 10. Everybody,
If you move it to the left, it'll be negative, right?
we did move it to the left. If we move it to the right, it would be negative. I'm going to get to that in a
Yeah.
minute. Yeah, let me do a couple of ones with positive first, and then we'll talk about the negative. Okay. All right.
You would never have to really put a small number like that in that notation, right?
Well, quick story. Back in, oh, I don't have it here. Back when I was a student in college, we used to use these. What this is a slide rule. Okay? This happens to be a circular slide rule. They have straight slide rules as well. I just don't know where mine is because I never use it anymore. And whenever you had to do a problem in a slide rule, using a slide rule, you always had to put the numbers in scientific notation. And I'll say one thing, having gone through it, I learned 2 things about using a slide rule. Number one, and I forgot to apologize for this. Number one, they're accurate to within 3 decimal places. Number 2, the second thing I learned about using a slide rule to multiply, divide, add, subtract. Well, you can't add and subtract, multiply, divide, do sines, cosines, stuff like that on a slide rule. The other thing I learned from my instructor who taught us how to use a slide rule is how sarcastic engineers are. Have any of you ever worked with an engineer before?
Yes.
No.
Yeah.
So if you've ever worked with an engineer, I think you can agree that engineers tend to be the most sarcastic, sardonic people on the face of the earth. I usually say SOBs on the face of the earth, but I won't because we're in a mixed company. My story about the slide rule and learning about engineers, I was in 10th grade, I guess it was. I was in a technical electricity and electronics program. And the instructor, who will remain nameless, showed us how to use the slide rule. And he told us on Friday there'll be an exam on the slide rule. So we all took the exam on Friday. And he comes in on Monday with the graded exams. And he says, how many of you passed the exam? And like out of a class of 20 people, I think 4 people raised their hands. So he said, those of you that passed the exam, you can go to sleep. Those of you that didn't pass the exam, how many of you used the slide rule on the exam? And we all raised our hands. And he said, okay. So how many of you that didn't pass the exam but used the slide rule on the exam didn't believe the slide rule and worked it out longhand? And he goes, how many of you that didn't pass the exam but used the slide rule and didn't believe it and worked it out longhand came up with a different answer than you got on a slide rule? Nobody came up with a different answer. So he says, let me get this straight. The reason you failed the exam is because you used the slide rule but didn't believe it, so you did the problem longhand. And we all went, yeah. And he goes, now those of you that failed the exam, used the slide rule, didn't believe it, redid the problem longhand, how many of you failed because you didn't finish? So he goes, so let me get this straight. You failed the exam because you used the slide rule but didn't believe it, so you did the problem longhand and didn't finish, and that's why you failed. And we were all like, yeah, all right, we get the point already. But he just kept hammering at us. And he goes, thank God he was a nice guy. He collected all the exams, ripped them up, and said, there'll be a new exam on Friday on the slide rules. He says, do I have to say anything about redoing the problem longhand if you don't believe your answer? And we all went, no. So that was my education about engineers. This was a guy who had worked on the Manhattan Project. He was an engineer. The Manhattan Project was the one that developed the atomic bomb during World War II. So he was one of about 47 bazillion engineers that worked on that. But yeah, so I learned about engineers on that one. That was an interesting thing. Anyway, so getting back to the original question, which went on this long tangent, do we ever have to put this into scientific notation? In today's calculator world, no. The one thing I will say about using a slide rule is there were 2 things that came up. Number one, you knew that the answer that you were getting, let's say you did a multiplication and you were in scientific notation. So let's say I multiplied this number down here times another number. This number can max out at 9.9999. The other number can max out at 9.9999. So you knew that when you multiplied these 2 numbers, it had to be less than 100. The powers of 10, if I multiply 2 numbers, the way we get the power of 10 of the product is adding the 2. So right off the bat, you had an indication of, are we talking about numbers in the thousands? Are we talking about numbers in the hundreds? Are we talking about numbers in the millions? Are we talking about numbers in tenths or hundreds or thousands units? We had that. So when we came up with an answer, if I multiplied 2 numbers and I knew that it was supposed to come up with something less than 100 times 10 to the 5th, let's say, and I came up with, 47 times 10 to the 23rd, I knew I made a mistake because you had to estimate your answers. I can't tell you how many times I have students today will pound numbers into a I had a student multiply 2 numbers. So it was like 5.8 times 9.2. I'm going to make up those 2 numbers. And he comes up with 578. I said, wait a minute. 5.8 times 9.2 is 578. He goes, yeah, look, and he pounds it back into the calculator again. And I went, no, think about it. 5.8 is about 6. 9.82 is close to 10. 6 times 10 is what? And he goes, 60. And he goes, yeah. I said, so if you multiply 5.8 times 9.2, you come up with, he goes 568. Look. Oh, one thing you had to do is you had to estimate your numbers. And it's one thing I'll say for slide rules. I would not advocate going back to slide rules, but it's one thing that I really feel is sort of missing from education today in terms of getting people to estimate their answers. Okay, enough digression. Let's go and look at a couple more examples. So let me do this before we leave this. If you move the decimal point right, power of 10 is positive. All right, so we moved left, excuse me. Do that again. If you move the decimal point to the left, like we did over here, the power of 10 is positive. If you move the decimal point right, the power of 10 is negative. Okay. So let's do a couple of examples. I'll give you a minute to jot that down. So let's say express 0.000123 in scientific notation. What we're going to do is we want to end up with the decimal point here. We want it to be to the right of the first non-zero number. So if I do that, I'm going to go 1, 2, 3, 4. So it's 4 places. It moved to the right. Therefore, we're going to express it as 10 to the negative 4th. So my number in scientific notation is going to be 1.23 times 10 to the negative 4th. Try this one. Try expressing those in scientific notation.
Sorry, the first one is 152837, right?
Pardon me?
The first one was 152837, right?
1928.
Oh, 19. Okay.
Yeah,
my bad.
192837. The bottom one is 0.00001127.
Is the last one 1,127 times 10 to the negative eighth power?
All right, hold on.
Nah, Chief. Nah.
How we doing? Everybody almost done?
Yeah, I'm done.
Let's take a look at them. If we look at the first one, where do we want the decimal point to end up? Well, first of all, we realize the decimal point is right there to start out with. So where do we want to end up with the decimal point? Between which two numbers?
In the 1 and 9.
We want to end up with the decimal point between the 1 and the 9. We want one non-zero digit in front of the decimal point. So let's see. We're going to move 1, 2, 3, 4, 5 places. To the left. So to the left means that we're going to have a positive power of 10. So we write it with the number with the new decimal point position. And now we're going to say times 10 to some power. And we just figured out it's positive 5 and it's positive. So we write that as 1.92837 times 10 to the 5th. Okay. Everybody with me? Questions? Okay. What about the second one? Where do we want the decimal? We know the decimal point is here to start out with. So where do we want the decimal point to end up? Between what two numbers?
Between both ones?
Between the two ones. We want to end up with the decimal point here so that when we're all set, I've got one non-zero number to the left of the decimal point. I'm going to move the decimal point 1, 2, 3, 4, 5 places. And we're moving it to the right, which means that it's a negative power of 10. So what we would do is we would write the numbers 1.127 times 10 to some power. 10 to some power. That power is going to be 5, but it's negative 5 because we moved it to the right. Okay, questions? Yes, no?
So,
No, not really.
Let's try 2 more and then we'll move on. Try those 2. Any ideas on the first one?
Yes.
10 to the 0.
Yeah.
Yeah, if we think about it, the decimal point is between the 1 and the 2. Where do we want to end up with the decimal point? Between the 1 and the 2. So how many places do I have to move the decimal point? 0 places. So we write the number 1.234, and the power of 10 we write it to is to the 0 power. Okay. What about the second one? Any ideas?
Same thing. Oh, no.
2.34.
2.34 times 10 to the third.
Okay, so we want to end up, the decimal point is here right now. We want to end up with the decimal point between having one non-zero number to the left of the decimal point. So we want to end up with it here. So we're going to move it 1, 2, 3 places. Right. Right means negative, right? So we're going to write the number 2.34 times 10 to the, and we just moved it 3 places. To the right means negative, so it's 10 to the negative third. Okay? Questions on that? Everybody follow why we came up with negative third for this one and how we got that it's 3? Yes?
Good. Yeah, we're good.
Okay. All right. All right, so let's take a look at what we call engineering. Well, there are what we call metric prefixes. So that means that we can use a letter abbreviation in place of the times 10 to the. So we already saw that if I had 1,000, that would be the same as 1K. We already talked about that last class, and you probably did a little bit with it in Professor Atwood's class. What we're really going to be interested, and there are a whole boatload of them. If you do Google metric prefixes, you'll see 10 to the 1, 10 to the 2, 10 to the 3, so on and so forth. But what we want to look at is something that's called engineering notation. And in engineering notation, we use a letter, or actually let's say it's a symbol because they're not all letters. To represent powers of 10 that are multiples of 3. So if we think about some of the common engineering prefixes, common ones we use is times 10 to the third is K, times 10 to the sixth is capital M. This was kilo, by the way. This is meg. This is gig.
Yeah.
Some of the common negative ones. Ten to the negative third is lowercase m, which we write as milli. 10 to the minus, we use the Greek letter mu. And we write or we speak that as micro. Ten to the negative ninth is nano, lowercase n. And 10 to the minus 12th is lowercase p for pico. So for example, if I wrote 22 megaohms, and let me explain this very quickly. Megaohms, people tend to lump them into one thing, like it's one thing. You have to remember that this is the base unit, and this is the engineering prefix. We get so used to saying megaohms as if it's one thing. Meg is like your power of 10. Ohms is the base unit. So if I had 22 megaohms, that would be the same as if I had 22 times meg is 10 to the 6th, 10 to the 6th ohms. So what we've done is instead of writing 10 to the 6th, we use the shorthand notation of capital M for that. If I had um, .8 microamps. The 2.8 is my value. Micro is the same as 10 to the minus 6th. And the units are amperes. If I had .47 picofarads, F F is the unit of farad, which is the unit of capacitance. You're going to learn a lot about capacitance next semester in ELT 115. So this would be the same as 47. Pico is 10 to the minus 12th. So we take out the pico and put in times 10 to the minus 12th. But the units are still farads. Okay, so if you want to think about it, the metric prefixes cover almost all of the powers of 10. The engineering notation is a subset of that in the sense that it only covers the powers of 10 that are multiples of 3. Okay? Questions up to here? Sometimes what we're going to need to do is we're going to need to be able to convert between units. And look, anybody need more time before I go to the next page? Hearing none.
Is the for Farah, is that like a P and then an F? So like subs.
Well, remember the P is the shorthand for Pico. So this
Gotcha.
replaces that, and the F is still the unit, so we bring the unit over. Okay, remember the P,
Gotcha. Thank you.
power of 10.
Okay.
Okay.
What's with the 47, by the way? Why many capacitors are in multiples of 47 pico nano?
Yeah, what it started out with is, if you go back to, if you think about the resistor color code, it sort of spills over to capacitors. The way that all started is, if you have let's say 5% or 10% tolerance, let's go back a ways, the resistors with a 10% tolerance. They said, okay, we'll start out with 10 ohms. What we need to do is we need to make sure there's between the lowest value of 10 and the next value, there's overlap, because what happens if I have a gap? So what they did was they said, all right, if I've got 10% tolerance and a 10 ohm resistor, that means that that resistor could be as high as 11 ohms or as low as 9 ohms. So let's make the resistor above it 11. And then they took that and said, all right, the next one's 11. Take 10%, what's the max of that? And make sure that the next resistor at least is equal to or overlaps slightly. So that if you came up with, let's say it did a calculation of, I need 472.8 ohms. Well, if even with overlaps, there was no 472.8, because one, let's say 460 was here and 510 was the next one. I'm losing my, because of the background. There would be a gap and you wouldn't be able to do it. You have to play games with all of that. But that's pretty much where that developed from. And it ends up with some weird values. One of the things I usually have my class do, and I'll probably have this class do, is make a list of all of the 5% standard values for resistors. And you'll see that they go 1, 1.1, 1.2, 1.3, 1.5, and then go from there. But that's where that came from, so that there's always overlap. It's a little strange, but it sort of works. Okay. You know what? I don't think I'm going to start this today. Let me give you a homework assignment. You get the textbook. Hopefully by now you've got the textbook. So in chapter, let me get rid of all this.
Professor?
Yeah.
Which textbook do you mean? Because I went onto the bookstore and I put in my, NCC number and such, and it said course materials has not been determined. So which is the textbook?
What do you mean? We told them a while ago that The book was Floyd. All right, so the book, let me write it out. Okay, so the text is Principles of Electric Circuits, Conventional Current. You have to be careful. There's two versions of this book, Conventional Current and Electron Flow. This is, not only the text disappeared, but I disappeared. All right, hold on a minute. Okay, so the text looks like that. It's Principles of Electric Circuit by Floyd and Buchla. Make sure that over here it says conventional current. That's the one you want, not the electron flow.
Professor, I'm opted into like the course, you know, the course, the NTC course program wherein they just charge you in exchange for book materials and so on and so forth.
Right.
Is there any way that you could reach out to the bookstore and let them know? Because I don't know if I'm the only one, but I'm on the bookstore like right now, and it's just saying that the course materials have not been determined for instructor Frederick Schoenfeld. So are we going to have to purchase this book on our own in addition to the course charge, or?
No, we'll definitely, you know what I'll do is, we know you're going to get it, the book, through the course thing. I don't know why. I will reach out to the department chair and ask her why it's saying that. I know I have something to ask about for my ELT 203 class. Something came up with that. So I have to talk to her about two. Let me see what I can find out between now and Monday. I'll hold off on the homework for now. Worst comes to worst, we'll do some of the homework problems in class. We'll do like a review, problem solving session, and let you go through some of the homework problems in class, and then hopefully the textbook should come up shortly. So, all right. And we're about out of time.
Okay.
So like I said, we'll hold off on the homework for now. And the thing we'll start with, excuse me, start with next class is the, how do we convert between powers of 10? So in other words, if I had kilo ohms and I wanted to know how many mega ohms that was, how do I do that? Or if I had picofarads and I wanted to know how many microfarads that was, how do I do that? We'll go through problems like that on Tuesday.
Would you have to double it then?
Double what?
Like, would you have to double the value?
No, it's gonna be. It's. I'm gonna leave it as the cliffhanger. You'll find out on Tuesday.
Okay.
Entice you to come back to class.
Okay.
All right. See y'all on Tuesday. Have a safe weekend. Stay safe, and see you on Tuesday.
Have a good one, Professor.
Okay.
Have a good one.
Good one.
Bye. Have a good
All right.
day.
Bye.
Bye.
Later, everybody.